So I wanted to kind of summarize what we've done in this unit. We had the overall goal, overall objective of modeling this speeding up motion. And I'm going to change that around a little bit. We need to build a model representing, instead of saying increasing speed, I'm going to say changing velocity motion. Just because it's more general, okay? Not just increasing speed. And our specific purpose, our first one, was what is the relationship between position and time? And this would be for an object that is changing its velocity. Okay? And we answered that already. We have an equation that represents how position and time are related for an object changing velocity. Now, this is our first specific purpose. We also have another one. Okay? So this is specific purpose number 1. Then we have a specific purpose number 2. Okay? It is what is the relationship between instantaneous velocity and time for an object that is changing velocity. Okay. So there's our second question, right? And the answer to our first question, why don't I separate these to separate pages? So first purpose, that would be this one, okay? When I grab this over, I'll group it together. So group, and then I'll copy it, and I'll put it on the next page, okay? I don't want this part. Yeah, that looks good. Okay, so we had a few different answers to this question. We got x versus t graph that looks like this. We have an x versus t squared graph that looks like that. And we have a beautiful equation. I'm just going to use this equation here on page 2. Get rid of this. Okay, so looks like my a value is 5, my b value is 0.1, and my c value is negative 0.2. So 5, 0.1, and negative 0.2. So we have an equation, position equals 5 meters per second times t squared. This is the equation of this curve, right? Now let's see what my b term was again. I already forgot. It was 0.1. Okay, so plus 0.1, and the units here have to be centimeters per second. 1 second. So it's 0.1 centimeters for 1 second because I have a t term there. And the units for this entire thing have to be simplified to centimeters. If you notice, this units here simplify to centimeters because I'm multiplying t squared. So if I plug in time, I get seconds squared, and my seconds squared are going to cancel here and here. So my units here cancel with my units here and here, and I'm left with meters because position is measured in meters. Now, this second b term has to be centimeters per second because centimeters per second has to cancel with my time term so that I'm left with centimeters, all right? And my last term, my c term, has to be in the units of just plain old centimeters. It looks like it's negative 0.2 here. You can see it right there. So negative 0.2, all right? So I get plus minus 0.2. And my units there have to be centimeters, simply because my units here have to match my units here. So everywhere, every term has to have the same units. Centimeters have to equal centimeters plus centimeters plus centimeters. And you wonder, what is this in general? Well, it'll be easier to figure out if we actually look at our velocity graph, okay? So our velocity graph turned out to look like this, right? And we got this equation, v equals, I think it was like about 10 centimeters per second per 1 second times t plus, I forgot what our intercept was. Let me find it. So I'm talking about this graph here. Looks like it's 0.1 centimeters per second. Okay? So 0.1 centimeters per 1 second. Okay? So this means this whole term is telling us at 0 seconds, our velocity of our object, was 0.1 centimeters per second. And we call this an initial velocity. And it's given a symbol v0. Okay? This term here, I wonder what that means. Well, you could say every second, our object has a specific change in velocity that occurs for every change in time. So every second, for example, our object changes velocity by 10 centimeters per second. And the units work because I have seconds here, seconds here. So every second, that takes care of that seconds. Our object changes velocity by 10 centimeters per second, and that accounts for those units. In physics, when we talk about a change in velocity that happens for every change in time, this is called an acceleration. So again, acceleration is a vector because it's a change in velocity divided by a change in time. And velocity is a vector. We take our final velocity vector and subtract from it our initial velocity vector. Take our final time minus our initial time. So, and another way of writing this is acceleration is found by finding the slope of our v instantaneous versus t graph. And you'll see that's the same thing as doing this. They are the same thing. And so in physics, we call this slope of our velocity time graph, we call it an acceleration. And you can see why this motion, the this model we've built is basically constant acceleration. So I should call this screencast constant acceleration motion. So I'll go back and say this is constant acceleration motion. And in the last unit, our velocity graphs were a horizontal line. But in this case, if you were to actually draw an acceleration graph, I'll do that at the bottom, I wonder what it would look like. Well, your acceleration time graph would simply be a horizontal line because we're dealing with constant acceleration. Now this line could be anywhere. We could have a negative constant acceleration or a positive constant acceleration, but that's more complicated. We'll get to that later. Okay, so we've essentially answered our question, but we haven't written our general equations yet. Okay, I'd like you to look at these two equations and try to imagine what the general equation is going to look like. Okay, and you can actually see it right here. We already said this was our initial velocity, okay, plus t, and we already said this was acceleration. So we have v equals acceleration times time plus our initial velocity. So that's our velocity versus time relationship. So we've answered how is time affecting instantaneous velocity. Now you would wonder, okay, what about our position time relationship? Okay, so we write x for position, that's this term here, right? Equals. Now if you notice, this 5 meters per second has the same, sorry, centimeters, this was centimeters. This has the same exact units as this, except it's 1/2. And that's because this is actually 1/2 our acceleration. And that's times time squared plus this term over here. Let's see what that term is. Well, the units seem to match our initial velocity. And the number is even the same as well. So that's pretty cool. So that means this must be an initial velocity times a time plus. And then finally that negative 0.2 centimeters, that sure looks like it has the units for position. So it's going to be a position at 0 seconds. And now we have a beautiful equation that represents how position and time are related when something's moving with constant acceleration. We also have a beautiful equation right here for how velocity and time are related when something is moving with constant acceleration. So two fundamental models for constant acceleration motion. I hope you liked the video, hope it helps you understand some physics, and I hope you have a good day.